Right, so we're gonna scientific method, which I know y'all have had before. And we're going to move through it pretty quickly. The scientific method is not going to be on any quiz. If you see it, it would be probably a couple of multiple choice when we do the test over the sheet. If you can't see something, let me know. Or if you can't read something, let me know. And then I can spell it out. All right, so starting off with the scientific method. So the scientific method is a logical solving problems by observing, collecting, data, formulating and testing hypotheses, and then formulating theories, and formulating theories, which are supported by data. And if you remember theories from biology, those are things that do have a lot of data that proves them or backs them up, but they can change as new things are discovered. So observing and collecting data, that would happen through experiments. So observation involved making measurements, and collecting the data, however you like to say it. Data may be qualitative, Q-U-A-L-I, T-A-T-I-V-E. Spell that one more time. Q-U-A-L-I-T-A-T-I-V-E. So that's data that's just descriptive. So like something's soft, something's blue. The data that we can kind of put can kind of understand a little bit better and is a little bit more important or a little bit more representative is the quantitative. Q-U-A-N-T-I-T-A-T-I-V-E. And so that would be your numerical data. So the measurements that you would be doing. Let's see that here. Experiments. Involve carrying out a procedure under controlled circumstances. So once again, I know y'all have had this before, but if you're carrying out experiments, they have to be controlled. So if I'm trying to figure out whether some kind of fertilizer makes the tomato plants grow more, the only thing I can be changing is fertilizer. If I'm changing the fertilizer and then I have one growing in here, one growing outside, one growing at the beach, that's too many different variables. So that would not be considered something that is controlled. If it's controlled correctly, you're just changing one thing at a time. And that's what you're measuring. All right, formulating, hypothesis. generalizations are statements that apply to a range of data. That next blank is generalizations. Again, I'm just putting little ditto marks, or you can put an arrow. Generalizations are used to form a hypothesis, which is a testable statement. It's often used as an if-then statement. So if I give the tomato plants more fertilizer, then will they grow more? Something that you can look at and see what the outcome is. So testing the hypothesis happens through experimentation, and it's used to support or reject a hypothesis. So we kind of act like it's always perfect and they're always supported, but in real life, a lot of the times they are not supported. So then the person that's doing the research kind of has to go back to the drawing board. So after that has been done, if it's been supported, then the next thing would be to try to form a theory. So a model is an explanation of how phenomenon occur and how data of events are related. Once that data, that experimentations happen and that data has been collected, then how can it be applied? So to do all of that, to do the experimentation, we need some quantitative data. So we need to be doing some measurements, and that's kind of what we're going to look at mainly today, because this unit is measuring matter. We did matter, and now we're doing measuring matter. So a quantity is something that has size, magnitude, or amount. It is not the same as a measurement. For one thing, a measurement's going to have units. Every number that we use, or maybe a couple here or there, would have to have units attached to them. They mean anything. If I'm looking at data and and my data is 3, 4, and 5 without a unit, I just have that data. That doesn't mean anything. So numbers without units are called naked numbers, and those do not happen. And there usually is a few people that don't like to put the units on it. Kind of takes a while for them to get to learn that. So the SI units, or the SI measurement, is just another name for System International. And it was adopted in 1960, obviously not for the whole United States, but for scientists, it was adopted in 1960. Before that, there were different systems being used, so it was hard to compare data if everything was not in the same system. Within the metric system, there are standards, and they have a constant value. So standards are what the units are arranged around. So for instance, if I measure something and I say it's 3 inches, that number only means something because I know what an inch is. That's the standard. And then when we measure things in inches, it's always measured around that amount. So that would be considered a standard. So these are the metric system base units. For length, it is L. And the base unit is a meter. Big M is abbreviation. Mass, little m, gram, I'm sorry, instead of gram being the base unit, it is kilogram. Or that's the standard unit. That is, a gram is very, very small. So anything that gets a little bit big, even like something like a baseball, then it's hard to apply grams to it. So kilograms would be a more realistic base or standard. And that is kg. Time, little t. We usually use seconds, s. Temperature, big T. Kelvin scale is the units for the metric system. And big K. So we'll do a unit next year, so second semester, where there's a lot of temperature measurements in it, and if the temperatures in Celsius, we have to change it to Kelvin. N, little n stands for the amount, and that is moles. And that's used mainly in chemistry, so you may not have heard about that before. The abbreviation is MOL, abbreviation. And the next one is electric current. We really won't use it. This probably is used more in physics. I is the symbol, and the name is ampere or amps. Probably something that we're more familiar with, and that is a big A. So probably the one that we use the most is mass and moles, and then secondary temperature and time. But we use moles a lot and we use mass a lot. All right, sometimes we will have what is called a derived unit. So that is a unit that has maybe 2 or 3 or maybe even more than that components to it. So it's a combination of base units. So we've done some kind of math and we multiplied or did it, or maybe both. So not only do we have to do that to the number, we would also have to do it to the units. So for instance, area is length times width. So not only do I need to multiply the numbers, I also need to multiply the units. So if that was in meters, when I multiply them, I would get meters squared. Volume is length times width times height. So in that case, you would be multiplying 3 numbers, excuse me, and also 3 units. So you would get cubic meter, which is meter cubed whenever it's written. Molar mass we use a whole lot, and that is grams divided by moles. So that's going to be a derived unit. We'll do density in this unit. And that is, its formula is mass divided by volume. So let's say that we measured the mass in grams and the volume in milliliters. Not only do we have to consider the numbers, we also have to consider the units. So that would end up giving us a derived unit. All right, so now we're going to move on into significant figures. I said we use those all year long. So once you've learned about them over the next couple of days, then you have to apply them. If you did not take the time to watch the video, I would really recommend that you do that because it can be pretty helpful. All right, let's talk about some sig figs. All right, so significant figures, they are used to indicate the precision of a measured number or to express the precision of a calculated number whenever you were using measured numbers to do that calculation. So unlike the numbers that you're using in math, our numbers that we use are different because they are applied to some type of measurement that we've taken. In any measurement, the digit farthest to the right is considered to be estimated. So if we say this is, we'll say these are inches. If you notice, the only thing that I can read, or 1, 2, 3, it would go on 4 and 5. I can only read those numbers. There's not any demarcations in the middle. So if I was trying to measure this line, the only thing I know for sure is that it's 1 and some other amount. I really only know the 1 for sure. The 0.3 is estimated. I may say 1.3. Does anybody think that looks like 1.4? We don't know for sure. It doesn't have a mark for us to decide. So this is not going to be a very precise instrument. Same thing. If I have 2, it's right here, my line. The only thing I know for sure is 2. The other one is estimated. I may think it's 2.0. You may think it's 2.1. And the fact that we use measurements instead of just numbers, that's the whole reason behind sig figs. So your calculation cannot be more precise than the digits given to you in a measurement. So for instance, if we're talking about density, we said that's mass divided by volume. But let's say that I did those measurements and I measured the mass and it was 2.2 grams. And then I measured my volume and it was 63 mLs. And I put that in the calculator. If I did that, I would get 0.0349206,349. Now, if you got that in a math class, you would round, maybe you'd write the whole thing down if that's what your teacher told you to do, or you would round it. With us, we have to decide which is a correct answer. If you looked at these two, those both had 2 significant figures. Now, if I look at this answer, if this answer is correct, then I had an instrument where I can see all of those, and my estimate was way down there. That would be an extremely precise number. So does it make any sense that my answer is that precise when my 2 measurements did not start off that precise to begin with? Does that make any sense to do a calculation? So that is what all sig figs is about. Our numbers we work with, we're given data, in a word problem or when we do a lab, and when we use them in a calculation, our calculation cannot show to be more precise than the measurements that were originally taken. It doesn't make any sense. So that's what we do when we talk about sig figs, applying them. So these are going to be the rules for your sig figs. It's also in that flow chart, which we'll go over some more, but yes, sir. Oh. You can very quickly. You'll have to catch up a little bit on the thing. All right, so let's talk about the rules. This is also on the flow chart, which I'll go over some more tomorrow. So all non-zero digits are significant. So when you're talking about sig figs, we're talking about zeros. That is the big deal. We're trying to decide if a 0 is significant or not. That's supposed to say 0. So this is our easiest one. If I have a number and it doesn't have any zeros, it's all going to be significant. So 125, no zeros. So that number has 3 significant figures. All zeros between non-zero digits are significant. So here, if I look at 101, the 0 I'm interested in is in the middle. So it sits at sandwiched, it would be significant. So that has 3 significant figures. I call these sandwiched or sandwich zeros. So I could have a number, I could have however many zeros I wanted in the middle. As long as there was a non-zero number on each end, everything is significant. So this one has 3, 6, 9, 12, 13 significant figures. So those are like the two easiest ones. So the next one says a zero following a non-zero and a decimal are significant. And there's some typos in here, and this is one of them. So if I look, this zero is not considered significant. That's considered a placeholder. These two zeros are behind a decimal and behind a non-zero number. So they are considered significant. So this would be 4 sig figs. If instead of that, I had that number, this number is always a placeholder. And that's how it is in math too. And you do not have to write it to be the correct answer. I tend to write it. These two numbers are behind a decimal. They are not behind a non-zero number. So those are considered placeholders. They are not significant. This zero is behind a decimal and behind a non-zero number. So it's considered significant. So these are my 3 sig figs. All right, zeros following only a decimal are not significant. So that's what I did right here. These are only following a decimal. They're not significant. These are only following behind a decimal, not a non-zero number. So they are not significant. Zeros following only, I know this is tight, only a non-zero number are not significant. So in other words, no decimal involved if it's just behind a non-zero number. So if I have 100, that is just 1 sig fig. If I have 5,000 grams, these zeros are just behind a non-zero number, so they are not considered significant. So this is just 1 sig fig. All right. Then the last one, the last digit is always an estimate. I mentioned that earlier. And trailing zeros. One. Only count if there is a decimal. So once again, that 100 without a decimal is 1 sig fig. But once I put that decimal in, it makes all of those numbers significant. This is another typo. So it should say 4 sig figs. 5,000 is 1 sig fig. 5,000 with a decimal becomes 4 sig figs. So the decimal makes a big difference on that. All right, so we are going to stop there. You can do some of your practice on the ones that you're counting. And like I said, look over that flow chart, and then we'll continue on tomorrow. If you did not watch the video, you have an opportunity to do that tonight. We do not have a quiz tomorrow. On Thursday, we'll have a quiz over classifying matter.